Everyone there? Cool. It started recording. We'll fire away. Sorry, you might need a head. Yes. Okay, some technical difficulties.
Robbie. We're playing Robbie.
It could be Robbie, Robert, Roberto.
Let's call him Roberto today.
Friday.
It's Roberto's day.
I think
Stefano.
we may just do a presentation like this. Okay.
We'll just
Okay.
have to be a bit closer and we'll read in.
Yeah. So today we're going to talk about interaction of X-ray with matter. In last session, we talked about X-ray production, and we learned that X-ray is produced when the moving electron are suddenly stopped at the anode, metallic anode. And there are two types of X-rays. One is Bremsstrahlung X-ray, that's also called as a Barking X-ray, and another is characteristic X-ray. Bremsstrahlung X-ray is produced when the moving electron interacts with nuclear fluid and change its direction. Whereas characteristic X-ray is produced when the moving electron strike the bound electron or the electron in the inner orbit of the metal target and eject that electron. And X-ray produced in X-ray tubes comes out of X-ray tube through a window made up of beryllium, which has copper and aluminum to filter out low energy X-rays. Because these low energy X-rays do not contribute in image formation, they will just increase the radiation dose to the patient. That is what we learned in last session. Today, we'll find out what happens to those X-ray that comes out of window of X-ray tube. And we'll also learn the interaction of X-ray with the matter in the molecular level. So what happens to that X-ray that come out of X-ray tube and interacts with matter? There are three possibilities. The first one is it get transmitted through the matter. Second, it get absorbed or scattered. Okay. The X-ray that get transmitted through the matter is detected by a detector. But interestingly, detector measure not transmitted X-ray, but absorbed or scattered X-ray. Did you get it, what I'm saying?
The bit that's missing.
No. So what happened is there is a matter. The X-ray interacts. It either get transmitted, scattered. It's showing here. It either get transmitted, absorbed, or scattered. Detector detect transmitted X-ray, but it measures absorbed and scattered X-ray indirectly. And how it measures, I'll tell you. So whole quantification of X-ray image based on the absorbed and scattered X-ray. Sorry. Oh, I'm sorry. Yeah. And this absorbed and scattered X-ray is called attenuated X-ray. And this process is called attenuation. And it's very important in medical imaging, this jargon, attenuation. So for example, OSIS implant is highly attenuating. What does it mean? It means that it either scattered X-ray or it absorbed the coming X-ray. So it's just attenuation, a lot of word in medical report, attenuation. And it is important for the quantitative analysis of X-ray. Yeah. Now, so how we measure X-ray attenuation? There are 4 different types of measurement. First is half value layer. Second, linear attenuation. Third, mass attenuation. And the fourth is Hounsfield unit, also called as CT number. So let us talk about half value layer. Half value layer is the thickness of matter that will reduce the intensity of X-ray by half. That's it. Very easy thing. So for example, if 10 centimeter thick matter decrease intensity of incoming X-ray by half, then half value layer of this material is 10 centimeters. So if we want to find half value layer of our titanium or stainless steel implant, then we should find the thickness of stainless steel that will decrease the intensity of X-ray by half. So how we'll do that? We just keep on scanning the different thickness of stainless steel and we'll find, for example, 2 millimeter is half value layer of our implant. So why it is important to find half value layer? It's important that because that half value layer will give us linear attenuation. So how we find it? If we divide 0.693 by half value layer, it will give linear attenuation of that material. Very easy. And the definition of linear attenuation, it's a bit sophisticated type of measurement as compared to half value layer, is the probability that the photon attenuates per unit length of path it travels in specified materials. But calculation is extremely easy. First, we'll find the half value layer, and then we'll divide. We'll divide 0.693 with that half value layer. And as you can see here, half value layer and linear attenuation are inversely proportional to each other. So if half value layer increases, linear attenuation decreases. If it is decreases, the linear attenuation increases. So is it clear? Is there any questions here?
What if you don't know what the material is?
What the material means?
What material that you're X-raying? Because you would need to know that.
Yes, we have to know that. I mean, it's all done by the computer nowadays. But if, for example, if somebody gives us some material and say that, can you find the linear attenuation of that particular material, then manually you can find it by finding the half value layer and then to the linear attenuation. And from this linear attenuation, we can find the mass attenuation now. But before that, just look at this equation. Linear attenuation is directly proportional to the density of the matter, atomic number of the matter, and inversely proportional to the energy of X-ray photon. So what does it mean? Linear attenuation, if energy is increased, if the photon energy is increased, the attenuation will be decreased because it's more penetrating. It won't scatter or absorb. That's the basic concept. Okay. Now let's talk about mass attenuation. Because in body, density is constant. We can't change density. We can't manipulate density. So if we divide linear attenuation by density, then we'll get a mass attenuation. So from half value layer, we can calculate linear attenuation. If we divide linear attenuation by the density of that matter, we can calculate the mass attenuation. And here, if you can see, mass attenuation is again inversely proportional to the energy of X-ray photon. And this is atomic number. Okay. Now we can calculate half value layer, linear attenuation, mass attenuation, and what about Hounsfield unit? Hounsfield unit can be calculated if we know linear attenuation of that particular matter. For example, OSIS implant. If we know the linear attenuation of OSIS implant, water and air. So how we can find the linear attenuation of implant, water and air? Ravi?
You go and find the half value layer. But
Exactly. So half value layer, linear attenuation, use this. We can use this equation and find the Hounsfield unit. But nowadays, all these equations are done by computer in the computed tomography. But this is the basic. So what we can use is, if there is a series of implant we have in one batch, and we want to know whether the linear attenuation are same or not, we can do by ourselves. So it will say whether the density is, similar or not, whether the atomic number is similar or not, whether what is the purity of the metal. So we can calculate all those things if you wish. So now in the second part of my presentation. In first part, if you have any questions.
Will, Izzy, Nat, you guys all good?
Yeah, all good.
Okay. So interaction of X-ray with matter. Now I'm going in more molecular or microscopic level. So what happened there? So there are 5 different types of interaction that can occur with the matter. First one is photoelectric effect. Second is quantum scattering. Third is coherent or elastic scattering. Fourth is pair production, and fifth is photo disintegration. I'll talk each of them individually. So let's start with the photoelectric effect. Photoelectric effect occur when the X-ray photon interact with the electron of inner orbit, bonding electron, K-cell electron, and it eject that electron. Okay, so when it eject that electron, this electron travels few millimeters in our body if we are scanning our body. And when we say radiation dose, this is the culprit. So whole dose is because of this electron. This electron is negatively charged. Our body is 90% of water. It will ionize that water. And that ionization is what radiation dose is. So it's not the direct X-ray that affect in diagnostic radiology. It's this electron that is creating, that is responsible for the radiation dose. First. Second, when the photon interacts with the inner cell electron, it loses all its energy. That means in photoelectric effect, there is complete absorption of energy. Complete absorption of energy. Photoelectron, this electron is called photoelectron. Photoelectron is responsible for radiation dose. And the third important point is that when there is a void, when the electron ejected from the inner orbit of the atom, there is a void here, the atom becomes unstable. So the electrons from upper orbit jump in the lower orbit, as in the characteristic X-ray. And the characteristic X-ray is released. That is very interesting phenomenon. So we scan our body part with the X-ray. Our body part itself starts to eject radiation, X-ray. But this characteristic X-ray is of no significance. It's so low energy, it can't do anything. It won't participate in image production, it is image formation, and also it's not responsible for any radiation dose to the patient. So we just neglect that one. But it's just interesting phenomenon. It's a characteristic X-ray. So just to restate that, the photoelectric effect, X-ray photon get completely absorbed. Photoelectron, that is ejected electron, is responsible for the dose to the patient because it ionizes water molecule. Characteristic X-ray produce, but it's of low energy and so doesn't have any significance. And now, how to calculate photoelectric effect? There is this equation. This is tau is a photoelectric attenuation density. Photoelectric effect is directly proportional to the density of material, its atomic number, and inversely proportional to the cube of X-ray energy. This cube of X-ray energy. The probability is highest when the X-ray photon energy is slightly above the electron binding energy, and it's obvious. No? If there is a binding energy, if we increase the energy of X-ray photon just little bit more than that binding energy, that will be sufficient to eject it. But if you see here, energy is inversely proportional to the photoelectric effect. That means if we increase the energy, photoelectric effect won't happen because it's inversely proportional. So is it clear? Okay. Then now we'll talk about. So I'll go to the Compton scattering now. So photoelectric effect is when X-ray electron interact with the inner shell electron, which is called bonding electron, very tightly bond with the nucleus of the atom. But in the contrary to that photoelectric effect, Compton scattering is the interaction with the outer shell electron. That's also called valence electron. Okay, free electron, loosely bound electron. What happens is the X-ray photon interacts with the outer shell electron and it changes its direction. It's called scattered. And it ejects that outer shell electron because it's easy to eject with little bit of energy. It doesn't need a lot of energy. And that electron travels again few millimeters in our body. And just like a photoelectron, this electron is also responsible for the radiation dose of the patient. Moreover, the deflected X-ray photon increase noise in image. So now what is noise? Noise is the image pattern that doesn't contribute any useful information. So we don't want noise. So for Compton scattering, X-ray photon hits free, loosely bound outer shell electron. Electron absorbs some of the photon energy and is deflected. The photon, having lost some energy, is deflected and scattered. So that is Compton scattering. So Compton scattering is interaction of X-ray with outer shell orbit and outer shell electron. Photoelectric effect is interaction of X-ray photon with inner shell electron. That is the difference. So now, yeah. So this is two equation. So I would like to focus you in these two, red circles. If you see, photoelectric effect is inversely proportional to the cube of X-ray energy, whereas Compton scattering is inversely proportional, but it is only with the energy of the photon. What does it mean? It's a very significant. Photoelectric effect is predominant phenomenon in low energy photon. So if X-ray photon is low energy, photoelectric effect starts. And again, high jet material, like if the material is with high atomic number, for example, contrast. So contrast, it is so attenuating because it is high energy. High atomic number. It has high atomic number. And in low energy, contrast give a lot of photoelectric effect. Okay. Whereas Compton scattering is predominant at high energy photon. But we have to remember, in high energy, overall attenuation decreases because the X-ray beam are more penetrating and the attenuation is less in that situation. Another scattering is cohort scattering, also called elastic scattering. So in this case, what happened is X-ray photon strike electron, but the energy of X-ray photon is not sufficient to eject it. So what will happen is it strike and get deflected. That is cohort scattering. Cohort scattering is around 5%. It will contribute only 5% for total attenuation. So it's less significant in diagnostic radiology. But just to know that cohort scattering or elastic scattering is when the X-ray photon is strike electron, but the energy of X-ray photon is not enough to eject that electron. Now pair production. Pair production occurs when the energy of X-ray photon is more than 1022 kilovolt keV. Okay, so generally in general diagnostic radiology, the maximum we can go is 140 keV. Above that, it's very harmful for the patient, and we don't use it. But if we keep on increasing the energy of X-ray photon, and if the energy of X-ray photon is more than 1022 keV, then a pair production occurs. What happens in pair production is, as the X-ray approaches near the nucleus of the atom, and it interacts with the nucleus, the photon energy changes into a matter. Energy change into matter. So it will produce electron. At the same time, it will produce so-called antimatter that is called positron. So two matter, same. Electron and positron are same. I mean, they have same mass. Everything is same. Only the charge is different. Okay. So that when the X-ray get disappeared, which is called annihilation, the terminology, X-ray annihilation, and produce matter, electron, and antimatter, positron. But this antimatter positron will travel few millimeters, and it interact with the electron. So positive positron interact with negative electron, and the matter disappear, and two energy appear, each 511 keV, exactly opposite to each other. The whole matter disappear and energy appear, opposite to each other, 511 keV. And we'll talk later on. And the PET scan actually registered this event. PET scan. So identification of this annihilation process and production of a pair of photons that identify by the PET scan is a basis of PET image. So we'll talk about that in later on in another session. So is it clear about pair production? So it's Einstein theory of energy changing into the matter and matter changing into the energy. And more, yeah.
If this doesn't make a lot of sense, spend a bit of time, and the textbook can be quite good on this, but also the slides, just analyze each of the sentences and sometimes maybe even go through the video again just to rewatch it.
Yeah.
It's a good way of
so I'll
touching
just
on the subject of PET scan, which is we'll go into later on, because the value in a PET scan is different to the value from a CT or an MRI. Yeah.
So maybe I'll just read out. Pair production occurs when electron and positron are created with the annihilation of X-ray photon. So it should be more than 10 megavolt. And the positron are very short-lived and disappear which is called positron annihilation, with the formation of two photons of 511 keV. It's not MeV, this is a typo, keV energy. And pair production is of particular importance when the high energy photons pass through the material of the high atomic number. So atomic number, yeah, should be high as well.
It's really exciting stuff.
And the final one is photo disintegration, which doesn't occur in diagnostic radiology at all. It's just to just to have some knowledge about it. When X-ray photon is extremely high, is of extremely high energy, more than 20 megafold. At that time, when it interacts with the nucleus of the atom, the whole X-ray energy is absorbed by the atom and by the nucleus, and the nucleus start to produce particles, alpha particles, beta particles. That is called the photo disintegration. But it doesn't occur in radiology, diagnostic radiology, because X-ray, the energy of X-ray photon is extremely high. We don't use it.
Is that in nuclear reactors or?
Yeah, I mean in nuclear reactor, yeah, it occurs. Yeah, nuclear reactor. Yeah. So in summary, attenuation is the amount of X-ray photon that is either absorbed or scattered. Photoelectric effect and quantum scattering are the two main interactions in diagnostic X-ray, diagnostic imaging. In low energy X-ray photon, photoelectric effect is dominant. High atomic number increases the chances of photoelectric effect. Example, contrast material, iodinated contrast material. And in high energy X-ray photon, quantum scattering is dominant feature. Thank you.
Any questions?
Which effect increases the dose the most generally of radiation?
You mean with photoelectric or quantum?
Yeah.
Photoelectric. Yeah, because in quantum scattering, what happens is that the X-ray photon also take some of its energy with it, so it's just diverted. So relatively, the electron that moves get less energy. Whereas in the case of photoelectric, effect, the whole energy is absorbed by that particular electron.
And you also have the other characteristic extract that's of less consequence.
So is the damaging side effects, are they accumulative, or does for a living cell, does it diminish? Does it cleanse itself at all, or is it?
Yeah, thank you. Good question. Actually, we'll talk about it in radiation dose. There are two types of effect. One is stochastic and another is deterministic. Name. Stochastic means it doesn't matter the dose. Once you are, once you get X-ray dose, independent of their energy, the chances of getting that disease is there. It will be there. Whereas in the deterministic, it is dose dependent. High dose, for example, cataract of the eye. So it is dose dependent. So if there is a certain dose, if we exceed that certain dose, cataract will develop. On other hand, cancer or leukemia, red blood cell aplasia, different type of cancer, blood cancer. It doesn't matter the dose itself. It's once you get X-ray radiation, the chances is there. So it's either you get it or you don't get it. Nobody can get it. So there are two different type of dose. Two different type of effect the X-ray can have.
So for our implant, it's really important that we have a high resolution scan. What kind of technology is occurring to improve resolution of X-ray or MRI?
Uh,
Or just X-ray, sorry.
Yeah, I mean, so basically, when we differentiate our implant from the surrounding soft tissue, implant is highly attenuating. We can see its border very clearly. The problem is with the soft tissue. So in the case of soft tissue, what we can do is to reduce the X-ray dose sufficient to penetrate the hip or leg, whatever we are scanning, but reducing X-ray dose will give a better subject contrast, better contrast between soft tissue, different soft tissue, whether the lipid, fat, muscle, ligament, skin. So the easiest way is to decrease the photon energy. Okay? But we should be very careful that the photon energy should be sufficient enough to penetrate, and there shouldn't be photon starvation. So less photon will again increase our noise. So that is another thing. We'll talk about that in other sessions.
So you want the energy to be low enough that you don't get as much Compton scattering or noise, but you don't want it to be so low that you get beam hardening or photon starvation. Or your implant goes and means you can't see the anatomy behind it.
So we should titrate. We should just, it's a heat and trial. There is no exact answer. We should try heat and trial, and we should find our own protocol based on our implant material, its density, its atomic number, all this thing.
Work to be done.
Yes, more work to be done. Just for the record, no one has to go and calculate Hounsfield units or centimeters.
Because if there is computer to do that,
Thanks very much.
just is understanding that what is Hounsfield unit.
I didn't see anyone taking notes. It's good.
Thank you.
Thank you very much.
Thanks.
That gives a bit of insight to how bloody complicated this is. It's great.
And the values we can pull from it.
Yeah, I was scheming when I was trying to get my head around how it works, and when you're talking about the implant and its thickness, is there some way of overlaying that, knowing the thickness of an implant through a section? It gets complicated, but I'm just wondering if there is down the factors.
Could look into it, definitely. Yeah. Cool.
So good.
Thank you.
You can go now, thank you.
Very much.
Thanks, Izzy, Nat, and Will.
Thanks.
Guys. Bye.
Bye.
Have fun on the coast.
Thank you. I was listening, but sorry.
Thank you.
And I wanted to get away. Nice weekend, everyone.
Well done, you